Our universe might be a single bubble floating in a vast cosmic sea. The search for how everything began takes us into the bizarre heart of quantum origins. We are about to explore 30 of the most fascinating theories that attempt to explain existence itself, from the strange rules of quantum mechanics to the very birth of space and time. These ideas sound like science fiction, yet they represent the serious frontiers of modern physics. By the end, you will understand the most compelling scientific arguments for how our cosmos came to be. We will investigate if our reality is a hologram or if time is even real. Which of these cosmic origin stories feels the most plausible to you? The story of our universe often begins with a single explosive moment. This is the Big Bang Singularity, the idea that everything we see around us was once compressed into a point of infinite density and infinite temperature. From that unimaginable state, space itself erupted and began expanding, cooling over billions of years to form galaxies, stars, and eventually us. The evidence for this event is compelling. We can still detect the faint afterglow of that primeval fireball as a static buzz of microwaves that fills the entire sky, known as the cosmic microwave background. Furthermore, we see that distant galaxies are all rushing away from us, their light stretched to redder wavelengths, telling us the cosmos is still stretching today. Yet for all its success, the Big Bang theory contains a profound mystery. The moment of the singularity itself is a complete breakdown of physics. Our equations of gravity and quantum mechanics simply fail when faced with infinite density. The theory describes the universe's explosive growth but offers no explanation for what triggered it or what, if anything, came before. It is a starting gun whose origin we cannot see. This fundamental gap is what pushes physicists to look for answers deeper than the bang itself, into the quantum realm where the rules of reality are rewritten. That singularity is a wall our physics cannot cross, but what if the Big Bang was not the true beginning, but merely a dramatic transition? To move beyond this wall, physicists proposed a breathtaking idea known as cosmic inflation. Developed by Alan Guth, this theory suggests that a fraction of a second after the universe's birth, it was seized by a strange new force, a kind of anti-gravity. This force caused space to expand at an unbelievable exponential rate, far faster than the speed of light. In less than a blink of an eye, a subatomic speck of reality was stretched to a size larger than our entire observable universe today. This violent growth spurt solved several major puzzles in one elegant stroke. It explains why the cosmos appears so remarkably smooth and uniform in every direction we look. Before inflation, any wrinkles or temperature differences in the infant universe would have been stretched so thin they became imperceptible, ironing the cosmos into the flat, even sheet we observe. But this process was not perfectly smooth. On the tiniest quantum scales, tiny fluctuations were inevitable. As space inflated at a fantastic rate, these microscopic ripples were also stretched, magnified into the faint seeds of all future structure. Every galaxy, every star, every planet we see today grew from those quantum whispers amplified by inflation's incredible expansion. The evidence for this is written in the oldest light we can see, the cosmic microwave background. Satellites have mapped its temperature with exquisite precision, finding the exact pattern of minute variations that inflation predicted. The theory also forecasts that this violent stretching of space should have generated powerful ripples in the fabric of spacetime itself, primordial gravitational waves. While their direct detection remains a goal for future observatories, their predicted signature is a cornerstone of the theory. Yet for all its success, inflation presents two profound new mysteries of its own. What was the engine, the specific field or particle that powered this explosive growth? And perhaps more puzzling, what caused inflation to suddenly turn itself off, allowing the slower, more sedate expansion of the Big Bang to take over? We are left with a universe born not from a single bang, but from a great, smoothing breath whose origin and end remain shrouded in quantum uncertainty. Inflation solved many puzzles, but it still points to a single beginning. What if the universe never truly began at all? The cyclic model presents a cosmos without start or end, an eternal engine of creation and destruction. Instead of a singular Big Bang, this theory proposes an endless series of Big Bangs, each one preceded by a big crunch where the entire universe collapses back in on itself. Imagine the cosmos not as a one-time firework, but as a great cosmic lung, eternally breathing in and out. Each outward breath is an expansion, giving rise to galaxies and life. Each inward breath is a contraction, pulling all matter and energy back into a hot, dense state, only to rebound in a new Big Bang. This vision elegantly sidesteps the troubling question of a first cause, replacing a definitive beginning with an infinite, repeating loop. Yet, the original cyclic model had its own problems. A universe collapsing into a big crunch would likely become incredibly messy and disordered, making a perfect, clean rebound impossible. How could a chaotic collapse produce the smooth, orderly universe we see today? Modern physics has revived this ancient idea with a startling new twist, one that exists within the strange landscape of string theory. This is the ekpyrotic model. It proposes that our entire universe is a three-dimensional membrane or brain floating within a higher dimensional reality. In this vast bulk space, there could be other brains, other parallel universes drifting nearby. The trigger for our Big Bang was not a collapse but a collision. Another universe, another brain, slammed into ours. This immense impact did not shatter reality, but infused it with an enormous amount of energy, heating it to an incredible temperature and setting off the expansion we observe. After the collision, the two brains bounce apart, slowly drifting through the higher dimensional void. Over trillions of years, they are drawn together once more by gravity, setting the stage for the next cosmic collision and the next cycle of creation. This process could repeat forever, with each bang and bounce erasing the disorder of the previous cycle, leaving a fresh, smooth slate for new galaxies to form. This idea transforms our cosmic story from a single, linear narrative into an epic without end. Are we living in just one chapter of an infinite book, our entire history destined to be reset and rewritten in a future collision? But the idea of a cyclical cosmos is just one possibility within a much grander framework. To find a deeper answer, we must shrink our perspective down to the very smallest scales, to the realm of string theory. Here, the fundamental building blocks of nature are not point-like particles, but unimaginably tiny, vibrating loops of energy. Think of a guitar string. Pluck it one way and it produces a specific musical note. Pluck it differently and you get another note. In string theory, these tiny loops vibrate in an infinite number of ways, and each distinct vibration manifests as a different fundamental particle. One vibration might be an electron, another a quark, and yet another the carrier of gravity itself. This elegant idea promises to unify all the forces and particles of nature under a single theoretical roof. Yet this beauty comes with a staggering consequence, a concept known as the string theory landscape. The mathematics of string theory does not point to one single universe with one set of rules. Instead, it suggests a truly vast collection of possibilities. The number of potentially stable universes it allows is almost beyond human comprehension, a number so large it is written as a 1 followed by 500 zeros. This is not just a handful of alternate realities. This is a near-infinite cosmic catalog where every possible set of physical laws and constants is realized somewhere. In this landscape, the force of gravity could be stronger, the speed of light could be slower, and the very nuclear forces that hold atoms together might not exist at all. Most of these universes would be stillborn, empty voids or chaotic messes instantly collapsing in on themselves. Our universe, with its just right constants that allow for galaxies, stars, planets, and life, is simply one winning ticket in a cosmic lottery of unimaginable size. The fact that we are here to observe it is not a planned outcome, but a statistical inevitability in a multiverse where every possible outcome exists. Does this mean our existence is a cosmic accident, a single fortunate bubble in an endless froth of failed realities? This cosmic lottery of the string theory landscape finds its perfect engine in the strange physics of inflation. We saw how inflation can smooth and stretch a universe, but what if its most profound effect is to endlessly create new ones? The theory of eternal inflation proposes exactly that, a cosmos where the process of exponential expansion never truly stops. Picture the fabric of space not as a single expanding sheet, but as a vast, bubbling cauldron. In most regions, the inflationary energy field decays, turning itself off to create a stable, slow-expanding universe like our own. But due to the random fluctuations inherent in quantum physics, some pockets of space never settle down. In these regions, the inflationary field remains potent, causing space to expand at a frantic, unstoppable rate. And within this rapidly inflating background, new pockets constantly form where the field does decay, each one becoming a separate, isolated universe bubbling into existence. Our entire cosmos, with its hundreds of billions of galaxies, would be just one of these countless bubbles, a single pocket in an infinite, ever-growing cosmic foam. The process is eternal, with no beginning and no end, continuously giving birth to new realities. This provides a breathtaking answer to the puzzle of fine-tuning. In this endless multiverse, every possible set of physical constants and laws will be realized in some of these bubbles. The strength of gravity, the mass of an electron, the power of the nuclear forces, all of these fundamental numbers are randomly set when each new universe forms. The vast majority of these pocket universes would be sterile, perhaps expanding too quickly for atoms to form, or collapsing instantly, or having forces too weak to build complex structures. We do not live in a special or designed cosmos. We simply inhabit one of the rare bubbles where, by pure chance, the numbers came out right for stars to shine, planets to coalesce, and life to eventually ask where it all came from. Our existence becomes a selection effect, a cosmic coincidence on an unimaginable scale. Are we the product of a universe so vast and prolific that even the most improbable outcomes are inevitable somewhere in the infinite froth? An infinite multiverse of pocket realities still requires a first cause, a primordial spark to ignite the eternal fire. But what if the ultimate origin is even stranger, a universe that literally created itself from nothing at all? This is the theory of quantum fluctuation from nothing, an idea that pushes the very meaning of existence to its breaking point. It begins with a bizarre but well-established rule from the quantum world, the principle of quantum uncertainty. On the tiniest of scales, empty space is not truly empty. It is a seething, frothing sea of potentiality. Pairs of virtual particles and their antiparticles constantly flicker into existence, borrowing energy from the void for an impossibly brief moment before colliding and annihilating each other, returning the energy and vanishing without a trace. This is not just theoretical, we can observe its effects in laboratory experiments. Now, take this quantum quirk and magnify it to a cosmic scale. Could the entire universe be the result of the ultimate quantum fluctuation, a single, monumental bubble of spacetime that popped into being from a state of absolute nothingness? This idea proposes that there was no pre-existing space, no time, no energy, not even the quantum fields that permeate our reality today. There was only a perfect, featureless void. From this true nothing, a quantum fluctuation occurred. The universe tunneled into existence, a tiny speck of reality born with a total energy of precisely zero. This seems impossible until you consider the ledger. The universe contains vast amounts of positive energy in the form of matter and radiation, but it also contains an equally vast amount of negative energy stored in the gravitational field that binds everything together. When you add them together, the total sum of the universe's energy may very well be zero. It all balances out. Our entire cosmos could be a monumental free lunch, a fluctuation that borrowed nothing and owes nothing, because its positive and negative energies cancel each other perfectly. This spontaneous birth would have been almost instantaneous, a quantum tunneling event that bypassed the need for a singularity and launched directly into the inflationary expansion we discussed earlier. Does this mean our magnificent universe, with all its galaxies and life, is fundamentally a grand and stable version of a virtual particle, a fluctuation in a void that simply never popped back out? Yet this idea of a universe born from nothing still assumes the reality of space and time as we know them. A more radical proposal suggests that even these fundamental experiences are an illusion. This is the holographic principle, the theory that our seemingly three-dimensional universe, with all its depth and volume, is actually a holographic projection of information encoded on a distant, two-dimensional surface. Think of the security hologram on a credit card. It looks like a three-dimensional object floating in space, but all of its information is stored on a flat, two-dimensional piece of film. In a similar, though far more profound way, the holographic principle suggests that everything we see and feel, every galaxy, every person, every event happening right now, is a projection from a vast cosmic film located at the boundary of the observable universe. The roots of this astonishing idea come from an unexpected place, the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, which is a measure of its information content, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon, the point of no return. This was a huge clue. It suggested that all the information about what fell into a black hole was not lost inside its vast interior, but was somehow encoded on its two-dimensional surface. Later, Leonard Susskind and Gerard T. Hooft took this a step further, proposing that this was not just a property of black holes, but a fundamental principle of the universe itself. The three-dimensional world we inhabit could be a projection from a two-dimensional surface at the cosmic horizon. This challenges our most basic understanding of reality. It implies that the world is not made of tiny, solid particles, but is ultimately composed of bits of information like the pixels on a cosmic screen. The solidity of your hand, the vast emptiness of space, the flow of time itself, all might be emergent properties of a deeper, two-dimensional reality. Are we living inside the most complex hologram imaginable? Our lives and history merely shadows cast from the edge of space. While the holographic principle reimagines our universe's dimensions, another theory rebuilds its very fabric from the ground up. Loop quantum gravity is a powerful competitor to string theory, offering a completely different path to uniting Einstein's relativity with the quantum world. This framework proposes that space itself is not a smooth, continuous backdrop, as we intuitively feel it to be. Instead, it is woven from an unimaginably dense fabric of tiny, finite loops. Picture the weave of an incredibly fine tapestry. Each individual thread is a loop of gravitational field, and the entire network of these interconnected loops, known as a spin network, forms the quantum structure of space. The fabric of reality is literally a mesh of one-dimensional threads. This has a profound consequence. Just as a digital image is made of a finite number of pixels, space itself is quantized. There is a smallest possible unit of volume, a tiny grain of space that cannot be divided any further. This discrete structure of spacetime completely changes the story of the Big Bang. In Einstein's general relativity, the beginning of the universe is a singularity, a point of infinite density where the laws of physics break down. But in loop quantum gravity, you cannot compress matter and energy into an infinitely small point because space itself has a finite, smallest size. You can only compress everything to that fundamental grain, At that ultimate density, the gravitational force, which is normally attractive, becomes powerfully repulsive. Instead of a catastrophic singularity, the universe reaches a point of maximum compression and then bounces. The Big Bang was not the beginning, but a transition, a great cosmic rebound from a previous collapsing universe. This is the Big Bounce. This theory provides a tangible, physical picture of a cosmos before our own. Imagine that previous universe not as some alien realm, but as a mirror of our own, following the same laws of physics. It may have expanded to a vast size, filled with its own galaxies and stars, before the pull of gravity eventually overcame its expansion, drawing everything back together in a great contraction. All that matter and energy was squeezed into the quantum grain of space, and then, repelled by the quantum nature of gravity, it sprang back out in the explosive event we call the Big Bang. Our entire history could be one chapter in an endless cycle of expansion, contraction, and rebirth, all governed by the quantum geometry of spacetime itself. The smooth geometry of a bounce offers one escape from a beginning, but Stephen Hawking and James Hartle proposed an even more elegant solution. Their no-boundary model completely reimagines the shape of reality to erase the need for a starting point altogether. It asks us to consider a universe with no boundary in time, just as the surface of the Earth has no edge in space. Think of our planet. You can travel across its surface in any direction forever without ever falling off a cosmic cliff. The North Pole is not a boundary or an edge, it is simply a point on a continuous, finite surface. Hawking and Hartle applied this same logic to the entire cosmos. They suggested that when we combine the three dimensions of space with the one dimension of time, the universe forms a closed, four-dimensional surface with no beginning and no end. To make this mathematically consistent, they had to introduce a strange but powerful concept, imaginary time. This is not time as we experience it, flowing from past to future. It is a mathematical tool, a different kind of dimension that behaves more like a direction in space. In this imaginary time realm, the history of the universe becomes a perfectly smooth, four-dimensional sphere. The Big Bang corresponds to a point on this sphere, like the North Pole on Earth. But just as the North Pole is not an edge, the Big Bang is not a violent beginning. It is simply a location on a continuous, seamless surface where the rules of our everyday time break down and transform. In this picture, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. The question itself loses its foundation. The universe does not have a creation story with a first cause, it just is. Its history in imaginary time is a self-contained, finite geometry without any singularities or boundaries. This proposal offers a profound answer to the ancient philosophical problem of a first moment. There was no first moment. The cosmos exists as a complete, unified object, and our experience of a linear, flowing time is a kind of emergent illusion, a shadow of this deeper, timeless reality. Does this mean our entire lives, from birth to death, are just a single, frozen path traced on the surface of an eternal cosmic sphere? The idea of a timeless, self-contained universe is a beautiful mathematical abstraction, but another theory brings the question of our origins crashing back into a startlingly human context. The simulation hypothesis proposes that our entire reality, from the most distant galaxy to the feeling of your own breath, is not base reality at all. It is an elaborate computer simulation, a virtual world created by a vastly advanced civilization, perhaps our own descendants trillions of years in the future. This is not just science fiction, but a serious philosophical argument first popularized by Nick Bostrom. He reasoned that if a civilization ever reaches a post-human stage capable of immense computational power, it might choose to run detailed simulations of its own history. These simulations could contain sentient beings with fully conscious experiences who would have no way of knowing they were living inside a program. If such a civilization runs even a small number of these ancestor simulations, the number of simulated minds would quickly and vastly outnumber the number of original biological ones. Therefore, statistically speaking, it is far more likely that we are among the simulated minds than the original ones. The scientific arguments for this idea often point to the strange mathematical nature of reality uncovered by quantum physics. The universe appears to run on a set of elegant mathematical laws, much like the code underlying a sophisticated video game. More compellingly, at the very smallest scales, space and time might not be perfectly smooth and continuous. Just as a digital image breaks down into individual pixels when you zoom in close enough, some theories suggest that spacetime itself has a fundamental, discrete scale, a kind of cosmic resolution limit. This pixelation of reality could be interpreted as the underlying hardware of the simulation. Yet for all its intrigue, the simulation hypothesis faces severe criticism. The most damning is its inherent unfalsifiability. There is no conceivable experiment we could perform from within the simulation to prove we are inside one, because any result we get could simply be part of the programmed rules. Furthermore, the computational power required to simulate every particle and force in an entire universe is staggeringly, perhaps impossibly, vast. Would even an advanced civilization bother with such an extravagant project? We are left with a profound philosophical choice. Is our existence a fundamental property of a self-contained cosmos, or are we merely data points in a grand computation? Our lives and loves just elegant lines of code in a universe we did not build. Our cosmic story may not be a linear narrative with a single explosive start, but an endless, repeating epic. Roger Penrose's conformal cyclic cosmology proposes exactly this, a universe reborn not from a crunch or a collision, but from a profound transformation of its own scale. In this radical vision, the universe progresses through infinite cycles called eons, each one lasting trillions of years. The astonishing twist is that the end of one eon seamlessly becomes the beginning of the next. As our universe expands forever, all matter eventually decays or is pulled into supermassive black holes. These black holes, over incomprehensible timescales, slowly evaporate away through a process known as Hawking radiation, releasing all their captured energy and information back into the cosmos. At this ultimate end stage, the universe becomes an almost featureless sea of low-energy radiation, devoid of any particles with mass. With no matter to define a scale, the concepts of distance and time lose all meaning. In this strange, smooth state, the universe's geometry can be mathematically rescaled or conformally transformed. The infinite, cold future of one eon becomes identical to the hot, dense, low-entropy state of a new Big Bang. The end is literally reborn as a new beginning, launching a fresh cycle of expansion, galaxy formation, and life. Penrose claims to have found evidence for this incredible idea imprinted on the oldest light we can see. He and his colleagues point to unusual, circular patterns of warm spots in the cosmic microwave background, which they call Hawking points. These are not the random fluctuations expected from inflation. Instead, Penrose suggests they are the final, fading imprints of supermassive black holes from the previous eon. In his model, the colossal burst of Hawking radiation released when those ancient black holes completely evaporated was imprinted onto the birth of our own universe, leaving faint, circular scars on the cosmic sky. This claim is, of course, highly controversial. Many cosmologists argue that these patterns can be explained by random chance within the standard model of cosmology, and that the entire concept of a conformal rescaling of time is mathematically problematic. Yet the idea persists, a beautiful and haunting vision of a cosmos where death is not an end, but a prelude to an infinite number of new beginnings. Is the entire history of our universe merely an echo of a forgotten past, destined to seed a future we cannot possibly imagine? Amidst this cosmic lottery of universes, a simple yet profound question arises. Why does our particular reality have such perfect conditions for life? The laws of physics seem suspiciously fine-tuned. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long before stars could form. If it were weaker, matter would never have clumped together into galaxies at all. The nuclear forces that bind atoms are also perfectly balanced. A tiny change would mean hydrogen would be the only element, or stars would burn out in an instant. This apparent cosmic coincidence finds its most debated explanation in the anthropic principle. This is not a physical theory in the usual sense, but a philosophical argument about our place in the cosmos. The weak anthropic principle takes a straightforward, almost humble stance. It states that we should not be surprised to observe a universe that is compatible with our own existence. Of course, we find ourselves in a region of the cosmos and a moment in time where the conditions allow for observers like us to arise. It is a simple statement of a selection effect. Imagine a puddle of water waking up one morning and thinking, "This hole I am lying in fits me perfectly. Its shape is exactly designed to hold my water." The puddle is missing the bigger picture. It is not that the hole was made for the puddle, but that the puddle conformed itself to the hole. In the same way, we are the puddles, and we simply conform to the cosmic hole we find ourselves in. The weak principle is a logical truism that is hard to dispute. The strong anthropic principle, however, makes a much bolder and more controversial claim. It suggests that the universe must have properties that allow life to develop within it at some stage in its history. This statement implies a sense of purpose or design, a universe that is in some way compelled to produce conscious observers. For some, this points toward a teleological argument, a universe with a goal. For others, it fits neatly with the idea of a vast multiverse. If an infinite number of universes exist with every possible set of physical constants, then it is inevitable that at least one of them will have the right numbers for life. We are simply in that one. The strong anthropic principle remains deeply divisive. Does it explain the universe's fine-tuning, or does it simply restate the mystery in a different form? Are we the intended outcome of a cosmic plan, or just the lucky winners of a random draw whose odds were infinitely stacked in our favor? While the anthropic principle debates our place in the cosmos, another theory asks a more fundamental question. What if the flow of time itself is not a basic feature of reality, but something that emerges from a deeper, more primitive structure? Causal set theory proposes exactly this, suggesting that spacetime is not a smooth continuum, but is fundamentally grainy, built from a vast collection of discrete atoms. Picture a universe constructed not from a fabric, but from a colossal, cosmic spiderweb of individual points. Each point represents a single, fundamental event in the history of the cosmos. These events are not scattered randomly. They are connected in a very specific way by a partial order that defines which event can influence another. This is the simple, powerful idea of causality. If one event can send a light signal to another, then they are connected. This web of cause and effect, this vast network of linked events, is the causal set. It is from this sparse, minimalist structure that the illusion of smooth, four-dimensional spacetime is supposed to arise. The immense number of these discrete points and the complex pattern of their connections creates a tapestry so fine that it appears perfectly continuous to us, much like a digital photograph appears smooth from a distance despite being made of individual pixels. This approach to quantum gravity is incredibly elegant because it starts with the one thing we know is real, the unbreakable chain of cause and effect. The theory's most profound implication may be its explanation for time's arrow. In our everyday experience, time flows inexorably from the past to the future, and this directionality is connected to the increase of disorder or entropy. But why does the universe have a past and a future at all? In causal set theory, the arrow of time is not built in from the start. Instead, it emerges naturally as the causal set grows. Each new event that comes into existence adds to the overall structure, and this process of growth, this continual addition of new points to the web, creates a natural direction from what has been to what will be. The growing universe itself manufactures the flow of time. The low entropy state of the early universe, the very thing that gives time its direction, could be a simple consequence of the universe starting from a very small, simple causal set. As it grew, the number of possible configurations exploded, and the universe naturally evolved from order to disorder, setting the cosmic clock ticking. Could it be that our relentless march from birth to death is just a side effect of a cosmos still under construction, adding new moments to an infinite web of causality? This concept of a growing causal set hints at something even more profound, a complete reinvention of what space and time actually are. The emergent universe theory proposes that space and time are not the fundamental stage upon which the cosmic drama plays out. They are the drama itself, emergent properties that arise from a more basic, non-spatiotemporal reality. Think of temperature. When you touch a hot stove, you feel a single, distinct sensation of heat. But that sensation does not exist at the level of individual atoms. Each atom is just jiggling around. Temperature emerges from the collective, frenetic motion of trillions upon trillions of these atoms. It is a property of the crowd, not of any individual. In the same way, the smooth, continuous expanse of space and the steady flow of time we experience might be large-scale illusions. They could be collective behaviors emerging from a vast network of something more fundamental, something that itself possesses neither location nor duration. This fundamental substrate is often imagined as a quantum information network, a kind of cosmic computer where simple bits interact according to basic quantum rules. Out of this chaotic, interconnected dance, the familiar geometry of spacetime condenses, much like a crystal forming from a cooling liquid. This completely reframes the Big Bang. It may not have been the absolute beginning of everything, but a dramatic phase transition. Picture a universe before what we call the Big Bang. It was not a smaller version of our cosmos, not a hot, dense ball in a pre-existing space. It was a formless, timeless quantum state, a seething ocean of potentiality where concepts like here and now had no meaning. Then a shift occurred. The system cooled or reached a critical threshold of complexity, and space-time as we know it crystallized out of this primordial soup. The Big Bang was the moment of crystallization, the point when the fluid, quantum world froze into the solid, classical reality of 3 dimensions of space and 1 of time. This phase transition would have released an immense amount of energy, igniting the inflationary expansion that shaped our cosmic horizon. In this view, our entire universe is like a vast iceberg that formed when the deeper quantum reality froze. We are living on the ice, perceiving it as solid and real, while beneath the surface lies the mysterious, fluid ocean from which it all came. Could it be that the very fabric of our existence is a kind of cosmic illusion, a stable pattern that emerged from a realm where the very ideas of place and moment are utterly meaningless? Our own cosmic home might be the interior of a black hole in a far grander reality. This is the startling premise of black hole cosmology, a theory that connects the birth of our universe directly to the most destructive objects we know. When a massive star collapses at the end of its life, its immense gravity crushes its core into an infinitely dense point, a singularity shrouded by an event horizon. From our perspective outside, anything that crosses this boundary is lost forever. But what happens from the perspective of something falling in? According to Einstein's general relativity, an observer crossing the event horizon would not notice anything special at that moment. They would continue their journey inward, drawn inexorably toward the central singularity. Now, take this idea to its ultimate conclusion. What if the entire region inside a black hole is not a dead end, but a new beginning? The crushing gravitational forces and the mind-boggling densities at the singularity could trigger a rebound, a transformation so violent it becomes a new Big Bang. In this view, our universe did not pop into existence from nothing, but was born from the catastrophic collapse of matter in a parent universe. Every black hole that forms in that cosmos could be the seed for an entirely new universe blooming in its own hidden interior. This creates a breathtaking fractal multiverse, a cosmic matryoshka doll of realities nested within realities. Our own universe, with its hundreds of billions of galaxies, could contain countless black holes, each one potentially harboring an entire cosmos of its own, completely separate and unreachable from our own. The laws of physics we observe, the strength of gravity, the mass of an electron, might not be fundamental constants at all. They could be inherited, emergent properties passed down from the specific conditions of the collapse that forged our parent black hole. Each new universe would have a slightly different set of rules, a unique fingerprint from its violent birth. This offers a compelling, natural explanation for the apparent fine-tuning we observe. We do not live in a universe magically designed for life. We live in one of the countless offspring universes where, by the random chance of its formation, the physics allowed for stars and planets to form. Are we merely one branch on an infinite tree of realities, our existence made possible by a stellar death in a universe we can never see? John Archibald Wheeler saw a universe far stranger than any multiverse or hologram. He proposed that conscious observers are not just accidental products of the cosmos, but active participants in its very creation. This is the participatory anthropic principle, a radical reimagining of reality where the universe only becomes real when it is observed. Wheeler, a towering figure in 20th century physics, was deeply troubled by the central mystery of quantum mechanics. In the quantum world, a particle does not exist in a single, definite location until we measure it. Before observation, it exists as a blurry cloud of probabilities, a superposition of all possible states. This wave of potential only collapses into a concrete fact at the moment it is observed. Wheeler took this bizarre rule and extended it to the cosmos itself. He asked a breathtaking question. Could the universe at its largest scales also exist in a state of fuzzy potential until a conscious being looks back and gives it a definite history? His most famous thought experiment, the delayed choice experiment, makes this idea terrifyingly concrete. Imagine a single particle of light, a photon, traveling from a distant quasar across billions of light years of space. On its journey, it approaches a massive galaxy whose gravity acts as a cosmic lens, bending the fabric of spacetime. The photon can now take two possible paths around the galaxy, like a traveler choosing to go left or right around a mountain. Back on Earth, we can set up a detector to observe which path the photon took. If we use a simple detector that shows us the particle like a tiny bullet, it will indeed reveal that it took one specific path, left or right. But if we change the experiment, if we set up an interferometer that allows the two possible paths to recombine, something miraculous happens. The photon no longer behaves like a particle that took one path. It behaves like a wave that took both paths simultaneously, creating a telltale interference pattern. The truly staggering part is this. Our choice of how to measure the photon, made billions of years after it began its journey, seems to determine which path it took in the ancient past. Our observation today retroactively writes the history of that photon. Wheeler argued that this logic could be applied to the universe as a whole. The Big Bang and every event since may have existed in a state of quantum uncertainty, a haze of unactualized history. Only when a conscious entity, like a human being, evolved and looked out at the cosmos, observing the cosmic microwave background or the light from the first galaxies, did that entire chain of events snap into a definite, concrete reality. In this view, we are not just living in the universe is living through us. It brought us into existence so that we could, in turn, bring it into existence by observing it. This creates a strange, self-excited loop where the cosmos generates its own observers to give itself meaning and form. Does this mean our quest to understand the beginning is, in fact, the very act that creates the beginning we seek to find? That same search for unity leads us to a theory that aims to be the master framework for everything, M-theory. Think of it as the ultimate version of string theory, the one that finally brings all the different versions under a single, elegant roof. The M stands for mystery, membrane, or even magic, and it lives up to that name by introducing a breathtaking new layer to reality. M-theory proposes that the fundamental ingredients of the cosmos are not just one-dimensional strings, but also higher-dimensional objects called brains. Our entire universe, with its 3 dimensions of space, could be one such membrane, a 3-brain, existing within a much larger, higher-dimensional space known as the bulk. We are like a slice of cosmic bread floating in a grand, multidimensional loaf. This single idea solves 2 of the deepest puzzles in physics in one stroke. First, it provides a stunning mechanism for the Big Bang itself. In this cosmic picture, our brain is not alone. Other brains, other parallel universes could be drifting through the bulk. The Big Bang may not have been an explosion from a point, but a colossal collision. Another universe, another brain, could have slammed into ours. This immense impact would have injected an enormous amount of energy into our membrane, heating it to an incredible temperature and igniting the expansion we observe today. This is the ekpyrotic universe model, a cosmic rebirth born not from a singularity, but from a shattering impact in a higher dimensional reality. The second puzzle M-theory addresses is perhaps the most perplexing question in all of physics. Why is gravity so unimaginably weak? The force that holds entire galaxies together is so feeble that a small refrigerator magnet can overcome the gravitational pull of the entire Earth. If gravity is a fundamental force, why is it trillions upon trillions of times weaker than the electromagnetic force? M-theory offers a beautiful and intuitive answer. While all other particles and forces, like light and matter, are open strings whose ends are stuck to our brain, gravity is different. The particle that carries gravity, the graviton, is a closed loop of string. Because it is a closed loop, it is not tied down to our membrane. It can drift away, leaking out into the higher dimensional bulk. From our perspective, trapped on our 3-brain, the force of gravity appears diluted, spread thin across dimensions we cannot perceive. Its fundamental strength might be similar to the other forces, but we only experience a faint shadow of its true power, a tiny fraction that has not yet leaked away. This explains its apparent weakness in our world. Are we living on a solitary island universe, or is our reality just one membrane among countless others, with the faint whisper of gravity the only hint of a vast, hidden cosmos lapping at our shores? The steady tick of time's arrow may be the most persistent illusion of all. The thermal time hypothesis proposes a radical idea that time is not a fundamental river flowing through the cosmos, but a kind of thermal shadow cast by the universe's increasing disorder. This theory suggests our experience of past, present, and future is an emergent property, a direct consequence of the universe's relentless march from order to chaos. Think of a cup of hot coffee sitting in a cool room. Heat will always flow from the coffee into the air, never the other way around. This one-way process defines a thermodynamic arrow of time for that small system. The thermal time hypothesis scales this idea up to encompass the entire cosmos. It argues that the flow of time we feel is generated by the statistical tendency of the entire universe to evolve from a state of low entropy, which is a high degree of order, toward a state of high entropy or maximum disorder. In this view, the clock ticks not because of some fundamental time dimension, but because the cosmos is, on average, moving from a more structured past to a more chaotic future. This completely redefines the Big Bang. It was not merely a moment of immense heat and density, but the state of lowest possible entropy the universe has ever had. The newborn cosmos was in an incredibly specific, highly ordered configuration, a pristine starting point from which it could only become more disordered. The expansion and cooling that followed, the formation of galaxies and stars, even the burning of fuel in our sun, are all manifestations of this one-way trip toward greater chaos. The arrow of time is simply the universe rolling downhill from that single, orderly peak. This leads to a profound conclusion about the nature of the beginning. If time emerges from thermodynamic change, then asking what happened before the Big Bang becomes a question without a foundation. The concept of before loses its meaning because time itself did not exist in that initial state of minimal entropy. The beginning was not a point in time, but the first and most ordered state from which time could then unfold. We are living inside that unfolding, our lives and memories tracing a path through the cosmic gradient from order to disorder. Is our entire history, from the first star to your last thought, merely a fleeting moment in the universe's long, slow sigh into equilibrium? The smooth continuum of spacetime might be a grand and convincing mirage. Quantum gravity proposes a universe that is not a seamless fabric, but a vast dynamic network of relationships, constantly rewriting its own rules of connection. Imagine the entire cosmos as a social network, where each point of reality is like a single person's profile. In the beginning, near the fiery dawn of the Big Bang, the universe was a frenzy of social activity. Every point was connected to every other point in a dizzying web of instantaneous links. In this hyper-connected state, the idea of distance was meaningless. There was no here or there because every location was, in effect, right next to every other location. This was a universe without locality, a chaotic, all-at-once existence where information could jump anywhere without delay. There was no space as we know it, only a seething graph of pure potential connection. Then, as the universe expanded and cooled, a cosmic freeze set in. Just as water crystallizes into ice when its temperature drops, this frenetic network of connections began to settle. Links between distant points were severed, while connections between immediate neighbors stabilized and strengthened. This process of freezing forged the regular, four-dimensional lattice we now perceive as spacetime. The three dimensions of space and one of time are not fundamental, but are emergent properties of this underlying graph's low-energy state. The speed of light, the ultimate cosmic speed limit, is not a law written on a stone tablet. It is simply the rate at which information can travel across this frozen network, hopping from one node to the next along the pathways that remain. This theory suggests that the vacuum of space is not empty at all, but is this very graph in its ground state. What we perceive as nothingness is actually a highly structured, low-energy network. If we could probe spacetime at incredibly high energies, we might find hints of this primordial connectivity, tiny defects or remnants in the graph that could reveal its true dynamic nature. Could our entire experience of a vast, spacious cosmos be an illusion born from a cosmic social network that decided, long ago, to settle down and freeze into a predictable pattern? Our cosmos might be a single link in an endless evolutionary chain. Lee Smolin's theory of cosmological natural selection offers one of the most provocative answers to the puzzle of fine-tuning, proposing that universes themselves evolve. In this breathtaking vision, black holes are not cosmic dead ends but cosmic wombs. Every time a black hole forms in our universe, the immense gravitational collapse at its core triggers the birth of an entirely new universe in a realm beyond our own. Each of these offspring is not an identical copy. As the new universe inflates into existence, the fundamental constants of physics, like the strength of gravity or the mass of an electron, are slightly tweaked, randomly mutated from their parents' values. This creates a vast, branching multiverse where the laws of nature are not fixed but subject to variation. Now, apply the logic of Darwinian evolution to this cosmic family tree. Which universes will be the most successful, producing the largest number of descendant universes? Those that are exceptionally good at making black holes. The formation of a black hole requires very specific conditions. You need stars, and for stars to form, you need galaxies, and for galaxies to form, you need matter to clump together in just the right way. A universe where the nuclear forces are too weak might not form any heavy elements. A universe where gravity is too strong might collapse back on itself before stars can even ignite. The universes that win the cosmic reproduction game are the ones whose physical constants are perfectly balanced to maximize the production of black holes. Our own universe, with its abundance of stars and galaxies, and its supermassive black holes lurking at the center of nearly every galaxy, is a black hole production powerhouse. According to Smolin's theory, this is not a lucky coincidence. We live in a universe that is fine-tuned for black hole production because it is the descendant of a long line of universes that were also fine-tuned for black hole production. It is a cosmic select. This elegant balance of cosmic accounts leads us to a theory of breathtaking simplicity. The zero-energy universe hypothesis claims that the sum total of all energy in the cosmos is precisely zero. Our magnificent universe, with its swirling galaxies and shining stars, might fundamentally be a grand statement of nothing. How can this possibly be true? It all comes down to a cosmic ledger of positive and negative energy. On one side, we have all the positive energy contained within matter and radiation. Every star, every planet, every particle of light represents a deposit into this account. This is the energy we are familiar with, the energy that powers our sun and our civilizations. But there is another side to this ledger, an entry of negative energy that is just as vast. This is the gravitational potential energy. Gravity is an attractive force, and it takes work to pull objects apart against its pull. This stored energy is considered negative. Think of a book resting on the floor. It has very little gravitational potential energy, but if you lift that book up to a high shelf, you have done work against gravity, storing energy in the book-Earth system. From the book's new perspective, its potential energy is now higher, more positive. But from the universe's perspective, you have created a more ordered state, and the overall gravitational field has become more negative to balance your effort. Now scale this idea up to the entire cosmos. The immense positive energy locked in all the stars and galaxies is perfectly counterbalanced by the even more immense negative energy stored in the gravitational field that binds them together. When you add these two cosmic columns together, they cancel each other out. The grand total is zero. This is not just a philosophical curiosity. It provides a stunningly plausible mechanism for the universe's origin from a quantum fluctuation. Creating something from nothing seems to violate a fundamental law of physics, the conservation of energy. But if the total energy required is zero, then no law is broken. A universe can pop into existence from a perfect vacuum, borrowing no energy because its final balance sheet is perfectly even. Our entire reality could be the ultimate free lunch, a quantum fluctuation that simply never had to be repaid. Does this mean that the majestic cosmos we inhabit is, at its heart, a magnificent and stable form of nothing? The quantum world holds a secret handshake that echoes across all of time. The transactional interpretation of quantum mechanics dares to suggest that every particle interaction, from a photon hitting your eye to a nuclear reaction inside a star, is not a single event but a settled agreement. In this view, when an atom emits a particle, it sends out an alpha wave radiating forward through time, a potentiality searching for a destination. But this wave is only half of the conversation. From the future, from every possible particle that could receive this offer, confirmation waves travel backward in time. The actual, definite event we observe, the particle appearing in one specific place, occurs only when an offer wave and a confirmation wave find each other and resonate in perfect agreement. This is the transaction, a handshake across time that crystallizes a single reality from a fog of possibilities. It is as if the universe is a vast marketplace of potential events, where deals are only sealed when both the past and the future mutually agree on the terms. Now apply this extraordinary idea to the cosmos itself. Could the entire universe be the result of the ultimate transaction? Perhaps the Big Bang was not a solitary shout into the void, but an offer wave of unimaginable scale, a wave of creation expanding forward from the beginning. And from the far future, from the ultimate fate of all that is, a confirmation wave travels back through the eons. This final state, whether it is a featureless heat death or a smooth, ordered unity, would then play an active role in shaping the very first moments of existence. The universe we have today, with its specific laws and constants, would be the one single reality that allowed for a perfect handshake between the first moment and the last. Our entire cosmic history, from the first star to the last dying ember, would be the settled agreement, the single transaction that resonated across time. Are we living inside a cosmic echo, a reality defined as much by its final destination as by its explosive origin? This cosmic fluid of connections finds its most abstract expression in a theory that rebuilds reality from pure mathematics. Group field theory proposes that the fundamental building blocks of the universe are not tiny vibrating strings or even loops of gravity, but something far more elemental, abstract atoms of space. These atoms are not physical objects in the way we normally think. They are mathematical entities described by the symmetries and relationships of something called a group, which is a collection of operations that can be performed without changing an object's essential nature. Think of a perfect sphere. You can rotate it in any direction and it still looks exactly the same. The set of all possible rotations is its symmetry group. In group field theory, each atom of space is defined by such a set of abstract properties, a tiny packet of pure geometric potential. The magic happens when these atoms interact. They do not simply sit next to each other, they bond together, merging their geometric data to build the fabric of spacetime. Imagine each atom as a single Lego brick with a specific shape and set of connectors. As these bricks interact, they snap together, and from their collective connections, the larger structure of space and time emerges. The smooth, continuous universe we perceive is the large-scale result of countless trillions of these discrete quantum bonds. This dynamic process completely redefines the Big Bang. It was not an explosion in a pre-existing void, but a dramatic phase transition within this cosmic quantum fluid. Picture a block of ice. At low temperatures, the water molecules are locked into a rigid, crystalline structure. But as you add heat, the ice melts into liquid water, a much more fluid and dynamic state. Now reverse that process. What we call the Big Bang could be the moment when a primordial, hot quantum fluid of space atoms cooled down and suddenly crystallized. Before this moment, there was no space and time as we know it. There was only a seething, chaotic soup of these fundamental atoms, a formless quantum foam where concepts like here and there had no meaning. Then, as the system cooled, the atoms began to bond in a coordinated, stable way. Space-time froze into existence. The immense energy released by this sudden crystallization would have ignited the violent inflationary expansion that shaped our entire cosmic horizon. In this view, our universe is not expanding into nothing. It is the crystallization itself, a frozen pattern that continues to grow as more quantum bonds form at its edges. Are we living inside a cosmic ice crystal, our perception of reality merely the stable face of a deeper, more fluid and turbulent quantum world? The unsettling truth is that you might be utterly alone, a momentary thought floating in an endless, mindless void. This is the Boltzmann brain paradox, a thought experiment that emerges from the cold logic of statistical mechanics and thermodynamics. It begins with a simple, undeniable fact: the universe tends toward disorder, a state known as high entropy. Yet we find ourselves in a cosmos of stunning order, with structured galaxies and conscious life. How did such a low entropy state arise? In an infinite or eternal universe, every possible random fluctuation must occur eventually, no matter how improbable. Given enough time, the random jostling of particles in a featureless, high-entropy void could, by sheer chance, assemble a fully formed, self-aware brain, complete with false memories of a past that never happened, hallucinating an entire universe around it. The mathematics are terrifyingly clear. The probability of a single, ordered brain spontaneously fluctuating into existence is astronomically low, but the probability of an entire, ordered universe like ours doing so is incomparably lower. In a truly eternal and infinite cosmos, there should be vastly more of these lone, disembodied Boltzmann brains than there are complex, coherent universes filled with observers. So, statistically speaking, you are far more likely to be one of those fleeting, solipsistic minds than a person living in a real, billions of years old universe. This creates a profound crisis for cosmology. If our best theories of an eternal or infinite reality predict that our own ordered existence is virtually impossible, then perhaps those theories are fundamentally wrong. The paradox forces physicists to seek out cosmological models that naturally explain a high probability for our kind of structured reality. Perhaps the universe had a definite beginning, setting a low entropy boundary that makes our ordered history far more likely than a random brain. Or maybe the laws of physics themselves are wired in such a way that they inevitably lead to worlds like ours, making us the rule rather than a statistical miracle. Are we the legitimate inhabitants of a genuine cosmos, or is every memory and sensation just the dying echo of a random fluctuation in an eternal sea of chaos? Two particles can be so deeply linked that the state of one instantly influences the other, no matter the distance separating them. This spooky connection, known as quantum entanglement, has long been one of physics' greatest puzzles. But what if this strange linkage is not a ghostly abstraction? What if it is a physical bridge, a microscopic tunnel through the fabric of reality? The ER equals EPR conjecture dares to propose exactly that, merging two of Einstein's most famous ideas into a single, breathtaking vision. The EPR paradox, named for Einstein, Podolsky, and Rosen, highlighted the bizarre, non-local nature of quantum entanglement. The ER bridge, often called a wormhole, was Einstein and Rosen's mathematical description of a shortcut through spacetime. For decades, these were seen as separate, unrelated concepts. One was a quantum oddity, the other a gravitational curiosity. But this new conjecture boldly states they are two sides of the same coin. Every pair of entangled particles is not just correlated by an invisible thread of information. They are connected by an actual, physical structure, a tiny wormhole. This bridge is not a tunnel you could ever travel through. It is unimaginably small, existing at the Planck scale, far beyond our current ability to probe. Yet, its existence would fundamentally reshape our understanding of the universe's architecture. The implications spiral out from the microscopic to the cosmic. Imagine the entire cosmos at its very beginning, a seething, hot, dense fireball. In that primordial state, every particle, every quantum of energy was entangled with every other. According to this idea, the infant universe was not just a point of immense density, but a complex, hyper-connected web of countless microscopic wormholes, a space-time foam of unimaginable complexity. As the universe expanded and cooled, these wormhole connections stretched and thinned, but they never truly broke. The vast, empty space between galaxies, which appears cold and isolated to us, might be threaded through with an invisible lattice of these quantum bridges, a hidden network of connectivity that underlies the apparent separation of objects. This provides a stunningly intuitive picture for how information can be non-local, traversing vast distances without ever crossing the intervening space. It simply takes a shortcut through the wormhole connection. The fabric of reality, in this view, is stitched together by entanglement, and the stitches themselves are these infinitesimal tunnels through the geometry of spacetime. Could it be that the universe is not a collection of separate things, but a single, deeply interconnected entity? its wholeness maintained by a cosmic tapestry of wormholes woven at the moment of its birth. Our universe appears to be expanding uniformly in all directions, a fundamental assumption of modern cosmology. Yet a strange and persistent signal challenges this cosmic principle. Astronomers have detected a mysterious, coordinated motion affecting entire clusters of galaxies, a vast river of matter streaming at incredible speeds toward a single point in the distant cosmos. This phenomenon is known as the dark flow. It is as if an immense, unseen hand is tugging at the fabric of our reality, pulling these colossal structures in a direction that defies all explanation from the matter we can observe. The force required for such a coordinated movement is staggering, and it points to something massive lying far beyond our observable horizon. One interpretation of this dark flow is as breathtaking as it is controversial. The gravitational pull might not be coming from within our universe at all. It could be the ghostly influence of another universe entirely, a separate cosmic bubble residing in the wider multiverse. This other reality would exert a tidal force on our own, tugging at the galaxy clusters like the moon pulls on the oceans of Earth. Another possibility is even more profound. This flow could be a cosmic fossil, a remnant from the era before inflation. Our universe's great smoothing might not have been perfectly even. A vast, pre-existing structure, a relic from the primordial chaos, could have left an imprint that still guides the motion of galaxies today. This would mean the dark flow is a whisper from a time before time, a directional memory etched into the cosmos during its first fleeting moments. The evidence remains hotly debated, with some scientists questioning the statistical significance of the observations. But if confirmed, the dark flow would force a radical rewrite of our cosmic story. It suggests our universe is not an isolated island, but part of a grander archipelago of realities, each one tugging gently on the others in the dark. The relentless pull of dark energy may not lead to an eternal, silent end. The Phoenix Universe model reimagines this cosmic force not as a death sentence, but as the very engine of an infinite cycle of rebirth. This specific vision of a cyclic cosmos proposes that dark energy, which currently accelerates the expansion of our universe, will eventually transform. In the far, far future, as the cosmos stretches to an unimaginable thinness, the properties of dark energy will subtly shift. Its repulsive force will weaken and reverse, becoming an overwhelming attractive force. This great reversal would slowly halt the universe's runaway expansion and begin pulling everything back together. Galaxies, now isolated islands of fading stars, would start a long journey home, drawn toward a final, universal collapse. This is not the messy, disordered crunch of old cyclic models. The key innovation here is dark energy's dual role. By driving a long period of accelerated expansion, it effectively erases the cosmic ledger. It smooths out the universe to an incredible degree, ironing out the wrinkles of structure and washing away the accumulated entropy or disorder from the previous cycle. The universe approaches its final state not as a chaotic jumble, but as an incredibly uniform, ultra-thin soup of radiation and particles. This pristine, low-entropy condition is the perfect starting point for a new Big Bang. The immense collapse powered by dark energy's new attractive nature culminates in a fiery conflagration, a bounce that does not simply repeat the past but truly renews it. The phoenix rises from its own ashes because dark energy meticulously cleans the ashes first, resetting the cosmic clock to zero and allowing the cycle to begin again, fresh and full of potential. This creates a truly self-sustaining, eternal cosmos, an endless loop of expansion, reversal, and rebirth, all governed by the changing nature of its most mysterious component. Are we living in just one of an infinite number of lifetimes for the cosmos, each one made possible by the very force we thought would be its final undoing? The primordial universe was a place of perfect symmetry, a state so unified that the four fundamental forces we know today were indistinguishable. This perfect harmony might have been governed by a hypothetical principle known as supersymmetry. It proposes a stunningly elegant structure for reality, suggesting that for every known particle in the Standard Model, from electrons to quarks, there exists a hidden superpartner. The electron would be paired with a selectron, the quark with a squark, and so on. In this supersymmetric state, the forces of nature merge into one. The electromagnetic force, the weak and strong nuclear forces, and even gravity would have been different facets of a single superforce. This was a cosmos of pure potential, balanced on a razor's edge. But such perfection is unstable. As the newborn universe expanded and cooled, it underwent a series of profound phase transitions, like water freezing into ice. The perfect symmetry of the superforce was broken. Supersymmetry itself collapsed. The partners of the familiar particles gained immense masses, shifting them into a realm far beyond our current particle accelerators. This breaking of symmetry was not a flaw, it was the creative act that shaped our reality. The energy released as supersymmetry shattered could have been the very engine that powered the universe's violent inflationary growth, smoothing it into the vast, flat expanse we observe. Furthermore, this rupture in the cosmic order may hold the key to one of existence's greatest mysteries: why we are made of matter at all. The early universe should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a sterile sea of light. Yet here we are. Supersymmetry provides a possible mechanism. The decay of the heavy, superpartner particles in the early cosmos could have violated certain symmetries, producing a tiny 1% excess of matter over antimatter. That minuscule surplus is all that remained after the Great Annihilation, the raw material for every galaxy, star, and planet. Our entire world might be built from the ashes of a broken symmetry, the faint leftover evidence of a universe that once knew perfect balance. Every quantum possibility exists until the moment it is measured, but we all share a single, stable world. How does this objective reality emerge from such a subjective, fuzzy foundation? Quantum Darwinism proposes a brilliant answer, suggesting that our classical world is shaped by a process strikingly similar to natural selection. In the quantum realm, a particle exists in a superposition, a blend of all possible states. It is both here and there, spinning up and down simultaneously. This fragile existence cannot survive contact with the outside world. When a quantum system interacts with its environment through even a single photon of light or a stray air molecule, most of its possible states are extremely fragile. They decohere, vanishing from the macroscopic picture almost instantly. But a few special states are robust. These are the pointer states, and they are the ones we actually measure and experience. They are the fittest in a Darwinian sense. Why? Because these particular states can be widely copied and recorded by the environment without being destroyed. Imagine you drop a single grain of pollen onto the still surface of a pond. The impact creates a complex pattern of ripples, a quantum superposition of possibilities. But only the most stable, symmetric ripples travel outward across the entire pond, imprinting their information on every water molecule they touch. The more chaotic, irregular ripples cancel themselves out immediately. In this analogy, the entire pond is the environment, and the widespread ripple is the pointer state. Its information has been replicated countless times, making it accessible to any observer. You do not need to be at the exact point of impact to know something happened. You can see the evidence in the traveling waves. This is the process of environmental einselection, where the environment itself acts as a selective pressure, choosing which quantum states are fit enough to be copied and become objective. In the early universe, this mechanism may have been the cosmic sculptor that carved a definite reality from a sea of quantum potential. As the primordial cosmos cooled and expanded, the relentless interaction between quantum fields and the dense, hot environment would have selected the first stable Poynter states. These selected properties, perhaps the specific values of fundamental fields or the initial seeds of density, were then amplified by inflation, becoming the classical bedrock upon which galaxies could later form. Our entire universe, with its definite laws and predictable behavior, might be the result of a grand, natural selection process where only the most communicable quantum states survive to tell their story. Are the solid objects and fixed laws we take for granted merely the most successful replicators in an ancient quantum competition? Our journey through quantum origins leads to a final, unsettling possibility. Perhaps time itself, the very stage on which our cosmic story seems to play out, is the grandest illusion of all. The theory of timeless quantum mechanics proposes that the universe does not unfold in a linear sequence of moments. Instead, all of reality, from the Big Bang to the farthest future, exists simultaneously as a single, frozen block. In this four-dimensional sculpture, the past is not gone and the future is not unborn. Every event, from the formation of the first star to your reading of this sentence, simply is, occupying a permanent coordinate in a vast static structure. The Big Bang is not a dramatic beginning in this view, but merely one particular configuration, one face of this eternal block. This picture emerges from trying to reconcile general relativity with quantum mechanics, and it presents a universe that is complete and whole, with no room for terms like now or then. The profound challenge this theory must overcome is our own undeniable experience. We feel time flowing, we remember a past that feels fixed, and we anticipate a future that feels open. How can this powerful, visceral sensation of a flowing present be reconciled with a timeless reality? The answer may lie in the nature of our own consciousness. Our brains are complex information processing systems that exist within the block, and our sense of a moving now could be a cognitive trick. As our memories accumulate, they create a narrative of a past, while our constant processing of new sensory data creates the feeling of a fresh, unfolding present. We are like a reader moving through a book, experiencing the story one page at a time, even though every page from the first to the last already exists bound together. The flow is not in the book itself, but in our act of reading it. This means your birth, your life, and your death are all equally real and permanent fixtures in the cosmic block. The universe did not begin and it will not end. It just is in one timeless, breathtaking totality. Does this mean our quest for a beginning was always an error, a story we told ourselves to make sense of a reality that is, in its deepest essence, eternally still? From the violent singularity of the Big Bang to the silent geometry of a timeless block, we have journeyed across 30 breathtaking visions of how everything began. We have explored universes born from collisions in higher dimensions, cosmic holograms projected from a distant screen, and even the possibility that our reality is a self-excited loop brought into being by our own act of observation. Each theory, from the well-trodden paths of inflation to the wild frontiers of the Phoenix universe and Boltzmann brains, represents a monumental effort to answer the most profound question we can ask. This incredible tapestry of ideas showcases the sheer creativity and audacity of the human mind, our relentless drive to push beyond the known and stare into the ultimate unknown. The quest to understand our quantum origins is more than a scientific endeavor. It is one of humanity's greatest adventures, a journey that stretches the very fabric of our imagination and logic to its breaking point. The conversation is far from over, and it is one we can all be a part of. Tell us in the comments which of these cosmic origin stories resonated with you the most. Which theory completely rewired your understanding of reality? If you enjoyed this deep dive into the foundations of existence, please like this video and subscribe for more journeys to the edge of our understanding. The universe is full of mysteries, and the next one is waiting for us to explore it